So we need to spend a little bit of time talking about waves and wave-like properties. Why do we care? Wave properties are how we describe light energy, and that's what electrons emit when they change energy levels is energy in the form of light. So this isn't just a physics detour, it's proof that light behaves like a wave. If I look at these, I've got interference, constructive and destructive interference. This is how waves behave. Constructively, they add up to make a larger amplitude. Destructively, they null each other out or they cancel one another out in a destructive interference pattern. When something passes through a diffraction pattern, it changes the direction of the wave. So diffraction is, you notice the slit here that it's going through. Let me write on the screen here. Diffraction is it's passing through the slit, and as I change the slit, it's changing the size and angle of what's passing through on the other side. And so that is a diffraction pattern. We've also got your two slit interference shown over here. And um, so it's two slit isn't just the two slit experiment is showing us that light is passing through two narrow slits. Okay, got light passing here and light passing here. Well, as it passes through, it spreads out and interferes, making bright and dark bands, which are your constructive and deconstructive or destructive interference. You're showing here, though, that light can bend, it can overlap, it can interfere. It's got classic wave behavior. Same thing here, properties of waves, they can go through refractive index. The wave diffraction pattern here, as it passes through a slit, it changes shape, but if a particle did, it doesn't change. Why do I care here? Well, it's this is very physics-like. Yes, it is physics. But we need to understand how light behaves as a wave because atoms interact with light and we use that light to measure and identify them. When electrons jump between energy levels, they emit light. That light behaves like a wave. So interference and diffraction aren't just physics for us, they're how we can prove that light is a wave and how we make sense of line spectra we see from the atoms themselves. The other thing about this is that we have this wave particle duality. That sounds like a weird concept, but basically what it is that an electron, light can do this as well, but we also know electrons can do this. They can behave as a wave, but they can also behave as a particle. If I have a wave that I pass through that that slit, okay, when it's a diffracted wave, it changes and it diffracts the shape of that species. It changes the shape of that light passing through. But if a particle passed through, if the particle hit the slit, it would just stop. Any particle that passes through would just continue on. And so what we find about electrons is that, again, they have wave particle duality, meaning electrons can behave as waves, but they can also behave as particles. When we treat an electron as a wave, it behaves as a particle. When we behave an electron as a particle, it behaves as a wave. So it's hard to study them because it's doing the exact opposite of what we're treating it as, right? But it's because electrons are so small and they're moving so fast that anything we do to it, to its environment, disturbs it and changes its behavior. So electrons have this wave particle duality. They can act as a wave, but they can also act as a particle. Brings us to this idea of the particle nature of light. So classic mechanics, chemical physics versus modern physics. Chemical physics was Newton, in 17th century, and he developed chemical physics. And chemical physics is extremely accurate for large objects or objects traveling well below the speed of light, which is not an electron. Electrons are incredibly small and they're traveling very, very fast. 20th century comes along, Einstein comes along, and he develops quantum mechanics and relativistic mechanics. So Einstein proposed that a beam of light behaves as it were composed of a string of small particles or packets of energy, and he called these packets a photon. A photon of energy, energy being E, is h nu, Planck's constant times the frequency of that particle that's traveling. The energy of a photon depends only on frequency, not on the amplitude, not on the intensity, not on the brightness. The intensity of light is corresponding to the number of photons. So if you have a really bright light, it's a lot more photons passing through, but it's not changing the frequency of those photons because they're coming from the same energy levels. An analogy to this is that a ping pong ball is thrown at a window won't break the glass, but one baseball would. So this brings us back to this particle nature of light. So we now see that light is acting as a particle, not just as a wave. We get this continuous versus quantized idea. Okay, a continuous spectrum. So, like, if you think back to the light spectrum we're talking about, a continuous spectrum is like white light. This is where you see rainbows. If it has rained and you look up in the sky afterwards and you see that pretty sky and you see a rainbow in the sky, you are seeing a continuous spectrum. You are seeing sunlight being diffracted through a prism through the rain droplets in the sky that are still there, and it's transferring it through, and it looks to you like a rainbow, but it's a continuous spectrum. There's no discrete lines in that rainbow. Quantized is like your stairs. There's absolutely specific energy levels where that species can exist. In a ramp, on a continuous spectrum, that ball's not going to stop anywhere. It's just going to go all the way to the bottom. It's going to be a continuous spectrum. But quantized, it's got very specific allowable energy levels. This is what I see for different elements or species in general, is see those discrete lines in the spectrum. Different colors corresponding to their wavelengths. So the main conclusions, the main point behind of this is that energy is quantized. In addition to behaving as waves, light also behaves as a particle. Energy is quantized, meaning it exists only in discrete amounts. So again, energy is quantized, meaning discrete amounts of energy. Quantum mechanics says that the amount of energy that can be transferred is quantized. I can measure it. Therefore, energy can only be transferred in discrete units of size, which are h nu, our Planck's constant times our frequency. So the energy transferred is directly proportional to our frequency. The smallest packet of energy is called a quantum, and an individual packet or particle of electromagnetic radiation is called a photon. So we've got these wave-like particle properties, right? So up until this point, scientists are indicating that light, which is wave-like, has particle-like characteristics. So de Broglie comes along, another scientist, and proposed, well, if energy is particle-like, then perhaps matter can be wave-like. And he developed the de Broglie equation. So again, the derivation is shown here. If you really want to go through it, I'll go through it pretty quickly, but I won't expect you to derive it. But we know that the energy of a photon is equal to h nu, our Planck's constant times our frequency, and that's Planck's law. We know Einstein's relativistic equation, energy is equal to mc squared. So we just set them equal to each other. If they're both equal to energy, we should be able to set them equal to each other. H nu equals mc squared. Or we know that nu, frequency, is also equal to speed of light over lambda. Therefore, hc over lambda must be equal to mc squared. We rearrange this equation and solve for lambda, and we get hc equals um, hc over mc squared. Cancel out the extra c's, and we get lambda equals hmc. But remember that Einstein's equation is mass, kilograms, that's our SI unit, and speed of light here. As we use lowercase m for mass and meters, so be careful with that. But this indicated that a photon with a wavelength lambda exhibits a mass, and this can be called your relativistic mass. For a particle traveling at a velocity v, we get the de Broglie equation. So instead of the speed of light, we just plug in the actual velocity of that particle. Lambda equals h over mv. Not new here, it's not frequency, it's velocity here. They look very similar, okay? So we can use Planck's constant times the mass of that species, or divided by the mass of the species divided by the velocity of that species. Basically, wavelengths inversely related to mass. The wavelength of a baseball is infinitesimally small because it's a big particle, while the wavelength of an electron is just about the size of an atom because an electron is so tiny. So let's go ahead and do a calculation. What is the characteristic wavelength associated with an electron moving at a velocity of 5.97 times 10 to the 6th meters per second? We're told, you would be told the mass of an electron here. I didn't give it to you in the question because you can always look it up when you're doing practice. But if I gave this to you on an assessment, I would give you the mass of an electron. I do not expect you to remember it, okay? I only remember it because of the number it is. So mass of electron is 9.11 10 to the minus 31st kilograms. And I literally only remember that because it makes me think of 911 and then Halloween, and people call 911 on Halloween. It's kind of a big night for it. It's a busy night. And that's how I think about it. But again, you need this in kilograms because of the way the equation is derived. Okay. So my de Broglie equation, you do have to know your de Broglie equation. De Broglie equation is Planck's constant over mass times velocity. You know your Planck's constant, 6.626 times 10 to the negative 34 joule seconds. We've got our mass of our electron, 9.11, 10 to the minus 31st kilograms. And our velocity here is given, 5.97, 10 to the 6th meters per second. When I calculate this out, I get 1.21, 10 to the minus 10th meters, which is the same as 0.121 nanometers. If it didn't specify, you could leave it in meters, but just converting it for you guys. Remember nano, 10 to the ninth nanometers for every 1 meter. Nano and 9 go together, the N and the N. Now, let's talk really quick about our units. How did our units get to here? Most students forget what their joules are, so don't forget what your joule actually is. Here we've got joule seconds over kilogram meters per second. But a joule is based on Einstein's equation, E equals mc squared. So mass in kilogram, and c is my speed of light. So meters per second, quantity squared, times second over kilogram meters per second. So one of my seconds, so this is the same as saying like meters squared, second squared. One of my seconds cancels here. My other second cancels here. One of my meters cancels here. One of my kilograms cancels here. And I'm left with meters overall. You guys should be able to do these calculations though. So you got some new constants